Okay, my people, in this video, we're going to focus on calculating expected counts for chi-square test for homogeneity and independence, the same as that calculation. Hopefully you just saw the Jason Molesky video giving you the first wave of attack of how to use this formula here. I'm going to do two examples. I'm going to do one by hand here using these numbers in here, and we're going to put the answers in this little table over here that says expected. And then we're going to show you a calculator technique using your TI-84. Okay, so to find an expected counts, we actually need four of them. So these are four observed counts. So we need the corresponding expected counts for each one of these items. And how do we do that? Well, you take the row total times the column total divided by the table total. So you can see if I wanted to find the expected count for this item right here, notice the observed is 7. I take the row total, which is 36, multiply it by the column total is 38, and then divide it by the table total, which is 117. So if I get my calculator right now, 36 times 38 divided by 117, I'm getting 11.69. So that's what I'm going to write right there, 11.69. That is the expected counts. Notice that's quite a bit of difference. Notice chi-squared statistic says what? That's the grand total sum of the observed amount minus the expected squared divided by the expected. So we're going to be adding up all of those differences to achieve the chi-squared statistic, which is a bit of a pain in the ass. Excuse me. So this particular video is just now focusing on what? The expected count for these four items. Let's calculate the next expected one. Well, the next one is going to be for 29. And so what would I do? I would take the row total, which is 36, times it by the column total, which is 79, divided by 117. And in that case, I'm getting 24.307. I'm going to put 31. How would I do the expected counts for 31 in here? Well, I take the row total, which is 81, times it by the column total, which is 38, and divide it by the table total, which is 117. So in that case, what am I getting? I'm getting 26.307. I'm going to put 31 again. And then the last one, which I'm going to do by hand, is what? I take the row total, which is 81, times it by the column total, which is 79, divided by the table total, and I'm getting 54.6923. So I'm going to put just 69. So all these are the expected counts, and those expected counts are used to calculate the chi-squared statistic. Okay, so let me just back up a little bit. There we go. So all four of those are used in conjunction with the observed ones to calculate the chi-squared statistic, which is something that we focused on in the first section. So that's how you find an expected count by hand. Okay, so let's do another example in here. And this week, in one of our social questions, I asked everyone, what was their predicted AHS return date? So I only asked people on Friday. I had 67 students respond. And notice I also asked you, excuse me, I didn't ask you, already know, your gender. So notice these are two categorical variables. This is gender, and this is the AHS return date prediction. And this is our values for the female, and this is the values for the male. Notice these are all observed counts. So we're going to find the expected counts using our calculator. So the first thing you have to do is to enter these 8 observed counts. Notice this is kind of feels like there's one list and another list, but when we deal with our calculator in this section, we do not deal with lists at all. We actually deal with matrices. So matrices can be entered on your calculator And in this case, this is what we call a 4x2 matrix. Notice the row number goes first, which is 4, and then the column number. Some of you may be going, Mr. Keys, I see 5 rows and I see 3 columns. No, you have to really understand that we're not going to be putting in the grand totals. We're just going to be putting in the 8 observed amounts. So that is 4x2. That's a matrix size. Notice 2x4 is not the same thing as 4x2. In this case, it is 4x2. So how do you enter that in your calculator? Well, where do you go? Well, there's a button down here called matrix. So to activate it, you have to go second matrix. And then there we go. So notice there's a couple tabs at the top. So right now we have these matrix names, A, B, C, and so forth. And I have already actually entered the information for matrix A, which is our observed amounts. The expected amounts, they're going to calculate for us, and they're going to prompt us where to put it. And they prompted me to put it in B, and so I put it in B. So how do you enter values? Well, you want to use this arrow over here, and you want to go over to the Edit tab, and then I want to edit matrix A. When I hit enter right now, I go into matrix A, and the first 2 values it's asking me is like, hey, what is the size of this matrix? And I entered 4, enter, 2, enter, and then I'm prompted to enter my observed counts. So that's what I did right here. I put 13, 21, 5, 1, 9, 6, 5, and 7. Notice, be careful when you enter these, you're not entering them top to bottom. You actually enter matrices across, and then you go down again. So hopefully you get some practice right now entering those 8 values. So you want to quit out of that. How do you do that? Well, you go second mode, which is second quit, and you get out of that. Whoops. Let me clear out of that screen. Okay. So in matrix A right now is that information. It's automatically saved for you. How would you fetch that information if you wanted to see if it's correct? Where you go second matrix. Don't go over to the edit tab now. Go over to the names tag and just hit enter when it's highlighted on matrix A. So when I do that, enter, notice it goes, hey, do you mean matrix A? I go, yes. I hit enter one more time. And notice it gives me the values that I just entered in matrix A. So that's how we enter values in a particular matrix. So to use our calculator effectively to find the expected counts, we now have to actually perform a chi-squared test. So how do we do that? Well, it's going to be under stat. So I hit stat. We've done this a million times. We go over to the test tab. And there's lots of different tests in here, that inference tests we've been using all year. I actually I scroll up, which goes down to the bottom and then goes up. I think that's the fastest way to find it. And it's just called chi-square test. Notice this is not a goodness of fit test. That's the first section. This is chi-square test. And we're going to use this procedural name for both the homogeneity and test for independence. So when I hit enter in here, it's quite simple. It's asking me, hey, what matrix letter or label did you put your observed counts? And I actually put them in A. So that's good. How would you, if A wasn't there, let me clear out A. If A wasn't there, what would you do? Well, you go to second matrix, and notice it's prompting me for A. I hit enter, and then it snaps A in here. This is not something that you type in. This is something that you fetch through the matrix menu. The next one usually is prompting you for matrix B, but you can make it any matrix you want. Notice I'm going to clear it out right now, and I'm going to tell it to put all of the expected counts in matrix B. So I'm going to go second matrix, scroll down to B, hit enter, and that's where it's going to put, when it does this test, it's going to calculate all the expected values for us, and it's going to put them in B. So the next thing I want to do is just scroll down to calculate, and here we go. I'm going to calculate. And when I hit calculate, it gives me some very important information that we're going to talk about later on. It gives me the chi-square test. Say thank you. That is pretty awesome. That's doing what? That's taking this subtraction, the difference between observed, expected, squared it, divided by expected, and it's adding it up for all 8 values. That's a whole lot of work. And that's our chi-squared test statistic. It's also giving us capital P here. This is our p-value. The p-value is fairly large in comparison to some other p-values we've seen. And that's going to help us make conclusions against alpha later on. And this is the degrees of freedom. We briefly spoke about the degrees of freedom earlier, which was what? The row number of values in the row minus 1, which would be 3, because 4 minus 1 is 3, times it by the number of values in the columns. And in this case, we have 2 values in our column. So it's 2 minus 1, which is 1. So 3 times 1 is 3. That's how they're getting this degrees of freedom at 3. It is 1 minus the rows times 1 minus the columns. Okay, so drum roll, where is the expected counts? So you have to find them or fetch them in your calculator. So you go second matrix, scroll down to B, and when you hit enter, this is going to be a big ugly mess. So when you hit enter and notice, this is giving us a lot of detail, which is nice. The AP board doesn't expect you to put all 7 or 8 decimal points in here. We're going to use the calculator, a feature that you probably never used before, to round all these to 2 decimal places. It's going to be easier to read, easier to see. It's not required that you do this, but it's going to be a nice helpful tool in the future. So I'm going to quit out of that. Keep in mind, what do I want to do? I want to round matrix B. So where is the round feature? Well, it's underneath the math feature in here. So I'm going to click math. And then the tab that says num, I scroll over. And then the second one down is round. So I'm going to activate round. And there's 2 arguments that this function needs that's called round. One, it needs to know what matrix letter you want to round. And then it wants to know how many decimal places you want to round to. So I'm going to fetch matrix B. I go second matrix. I go down to B. Notice it snaps B in there. Then you have to put a comma and then the number of rounding that you want to see. So in this case, I want to round to 2 decimal places. I put a 2 in there, close parentheses, get into a good habit, and that's the 2 arguments separated by a comma that this round function needs. When I hit enter, notice these are the values. And so I'm going to now copy those values into my little table over here. So 16.24, I'm going to write 16.24. And what's the next one? 17.76. 17.76. What's the next one? 2.87. 2.87. And this is 3.13. This is 7.16. 7.87. And we got 2 more left, 5.73, 5.73. Then the last one, 6.27. Hopefully you're being much neater than I. Okay, so that is the expected counts. And notice, we could have done this by hand. We could have taken what? For this position right here, we could have taken 34 times 32 divided by 67. I want to do it on my calculator right now. I'm going to go 34 times 32 divided by 67, and I'm getting 16.238. So 16.238 is now rounded to 16.24. So please get some practice when you're calculating the expected counts with your calculator. It's kind of an interesting question. We haven't talked about whether or not this is a significant difference between females and males in here, but we certainly explored how to calculate expected counts, and we're trying to see if there's an association between gender and the return date of the predicted return date back to AHS. Here's a side-by-side bar graph as well. So you can see the two-way table comes to life, and you can see males are more extreme than females with this visual summary. Notice there's much more males, many more females compared to uh, males compared to females when we're asking them about the August 19th or the May 4th. So those were the earliest dates or the latest dates of the four options I gave you. You can see males like the extremes. They're like, hey, all or nothing. Hey, we're going back as soon as possible, or we're going back late. Most people, you can see by the height of these two graphs, and again, these are counts. These are not proportions. Notice we had two different column totals in here. These are similar, and meaning they are close to the same number, but these can be very deceiving. If I have 3,500 versus 32, I would have a very large observed amount for red and a very small one for blue. If I use the relative frequencies, meaning the proportions, I would get something similar to this because these two numbers are the same. So you can see um, the reason why we like to use relative frequency graphs when comparing two columns in here of different sizes. These are fairly close. I just happen to graph the observed counts in here, and I don't think it's too misleading. But you can see it's very easy to mislead people using observed counts. All right, so let's stop the video here, and we'll talk more about the details of the two tests when I come back.